Welcome to Naradar Academy. In this video, we are going to discuss about friction and few problems based on friction. Friction means roughness. Okay, it is always a contact force. See, whenever two bodies are in contact with each other, okay, they may slide one over the other or they may be at rest. Okay, if they are at rest means the roughness of one surface prevents the other surface from sliding over the other. Okay, this roughness is called, that property of roughness is called friction. So every surface will have friction. It may be very less for smooth surface and very high for rough surface. Okay, so it is always a contact force. Now the friction is classified into three types: static, dynamic and limiting friction. Static friction means when both the bodies are at rest, that is in equilibrium position. So the friction exerted between them, no, that is called static friction. So here in this case the friction is just enough to maintain the equilibrium. So it is very less and it is enough to maintain the equilibrium. Okay, next one is dynamical friction. So this dynamical friction is uh, dynamical friction exhibits when one body is moving on the other. Okay, so here also friction is there. So by uh, going through the friction, it is moving one body over the other. Okay, this is called dynamical friction. Apart from these two, there is one more friction, that is called limiting friction. This limiting friction means initially the bodies may be at rest. When one point is just on the point of sliding over the other, that kind of friction is called what? Limiting friction. So the friction will be maximum only in this case. Okay, so here in this video we are going to discuss more about this limiting friction only, right? So here when will you have this case? When one body is just on the point of sliding. Okay, so in this case the friction is maximum and it is called limiting friction, and the equilibrium is called limiting equilibrium. So the motion is not yet started. Okay, still the bodies are in equilibrium, so the equilibrium position is called limiting equilibrium and the friction exerted is called limiting friction. So in this particular case only we are going to discuss throughout this video. So here we have coefficient of friction. Coefficient of friction is denoted by mu and it is the ratio between F and R. So what are these F and R? F is the friction and R is the normal reaction. So what is this normal reaction? See, whenever we place one object over the other, the weight of the body will be exerted, no? So for that weight, there will be equal and opposite reaction. So that is the normal reaction, that will be always perpendicular to the plane, and that is my R, and this is my friction. Friction will always be opposite to the direction of motion. If your body starts moving along this direction, the friction will be in this side. Okay, so this is my friction and this is my normal reaction. The ratio between the friction and the normal reaction in limiting equilibrium. Okay, in that particular case the coefficient mu is equal to F by R. This is called coefficient of friction. Okay, otherwise we can say mu is equal to tan lambda. What is this lambda? It is the angle of friction. So where do we find this lambda? See, this is the friction, this is the line of action of the friction, and this is the normal reaction. You find out the resultant of these two by using parallelogram law. That is the resultant of this F and R. So by parallelogram law, it will be along the diagonal of this parallelogram, no? So this is the resultant of the friction and the normal reaction. This resultant is making an angle lambda with a normal reaction, and this lambda is called the angle of friction. So the coefficient of friction can be written in two ways, either F by R or mu equal to tan lambda. So all these things are applicable only when the friction is in limiting case, that is limiting equilibrium. Okay, so I have explained what is angle of friction. Then the next one is cone of friction. So what is meant by cone of friction? See, this is the friction mu R and this is the normal reaction. So this will be my resultant of friction and normal reaction, and this is the angle of friction. With this angle as the semi-vertical angle and the normal reaction as the axis, you draw a cone, and that cone is called cone of friction. Okay, the semi-vertical angle is equal to what? Lambda, angle of friction, and the normal reaction will be the axis of the cone. Such a cone drawn is called cone of friction. Now we have 5 laws of friction. So whatever we have studied already, they will be consolidated here. These are called laws of friction. So when two bodies are in contact, the direction of friction on one of them at the point of contact is always opposite to the direction in which the point of contact would commence to move. Okay, so the friction is always opposite to the direction of movement. This is the first law. Second law, when the body is in equilibrium, the magnitude of friction is just enough to prevent the body from moving. Okay, so just it is enough to prevent the body. Second law, this is the second law. Then third law is the magnitude of the limiting friction always bears a constant ratio with the normal reaction, and this depends on the substance of which the bodies are composed. Okay, so the ratio between friction and the normal reaction is always a constant. Okay, then next one is the limiting friction is independent of extent and shape of the surface in contact, so long as the normal reaction is unaltered. So this is very important point. The friction is independent of the extent and shape. So there is no relation between extent and shape of the body with friction. So it is independent. It is only dependent on the substance of which the bodies are composed. Okay, the material with which the bodies are composed. Then the last law is law of dynamical friction. So when motion ensues by one body sliding over the another, the direction of friction is opposite to the motion. The magnitude of friction is independent of velocity of the point of contact. Okay, so the friction is independent of velocity also, but the ratio of friction to the normal reaction is slightly less when the body moves than when it is in limiting equilibrium. So in the fifth law, what do we say? Again, the friction is independent of the velocity while it is moving, and what we say, the ratio F by R, it will be slightly less than in limiting equilibrium. Okay, so these are called the 5 laws of friction. Now let's see one problem. A particle of weight 30 kg resting on a rough horizontal plane is just on the point of motion when acted on by a horizontal forces of 6 kg of weight and 8 kg of weight at right angles to each other. Find the coefficient of friction between the particle and the plane and the direction which the friction acts. So I have a body and its weight is 30 kg. So whenever I am placing this body on a floor, it will exert a normal reaction. So that normal reaction will be perpendicular to the plane. Okay, so if it is this weight is 30 kg, then the normal reaction will also be of magnitude 30 only. Okay, now let's come to this diagram. So here my object is there. This object is acted upon by two forces. One is 6, another one is 8, magnitude 6 and 8. So they are acting horizontally and vertically. One is along horizontal direction, another one is along vertical direction. Okay, right. Find the coefficient of friction between them. So in limiting equilibrium, what is F and R? That is what we want to find. Now what you have to do in this case is find the resultant of these two. Okay, see the body is placed here. Even after applying these two forces, the body is still at rest. Okay, that means what? The equal amount of friction is exerted. So find out the resultant of these two forces. How will you find the resultant? So this is a rectangle, you know. So the resultant is equal to square root of 6 square plus 8 square. I am applying parallelogram law. So it is equal to 36 plus 64 equal to root 100, which is equal to 10. It will be along the diagonal of the rectangle. So 10. So at this point of the body, I am applying a total force of 10 units along AC. But even after applying this force, the body is not moving. That means the friction is there. Where will you represent the friction? It will be opposite to the resultant. So the resultant will be along this direction. So that means what? Actually, if the force is enough, then the body have to move along this direction, but it is not moving. That means friction is pulling it this way. Okay, so this is my friction. So what will be the value of the friction? It will be equal to this magnitude. Then only it can prevent the body from moving. So the friction is equal to 10 units. Then what about the normal reaction? Already I have explained you. So whenever you are placing a body, the equal force will be exerted here. So R equal to 30. So F and R I know. So mu, the limiting friction by the normal reaction, equal to coefficient of friction. Mu equal to 10 by 30 equal to 1 by 3. So this is the coefficient of friction. Right, and then what about the angle of friction? Angle of friction is the angle between the resultant and the normal reaction. So this is lambda, tan lambda equal to opposite side by adjacent side. Since this is a rectangle, 6 by 8. So what will you have? Lambda equal to tan inverse of 3 by 4. So this is the angle of friction. Okay, next. Next here, we are going to discuss three types of problem in this video. Here, that is, we are going to talk about particle placed on a rough inclined plane. The first case is equilibrium of a particle on a rough inclined plane under the action of the weight itself. That is, there will be no force acting along the plane. No external force is there. Only I am going to have, see, this is a horizontal line. Here I have a plane which is inclined at an angle theta to the horizontal. On this plane I am placing a weight of W at this point A. So what are the forces will be coming to act here? It's weight W which is acting perpendicularly downwards and normal reaction. See, whenever a weight is placed on an inclined plane like this, the normal reaction will be perpendicular to the plane, not perpendicular to this line. It will be perpendicular to the plane. Okay, so perpendicular to the plane, here I will be having the normal reaction. Now I am assuming the body is in equilibrium. That means, see, whenever you place a body here, it will come down, it will slide down, no? So if it is not sliding down, that means what? The friction is more. So where will you have the friction? It will be along upside the plane, because if no force is applied here, the body will come down actually. So if the body is coming down, the friction will be always in the upward direction. So only three forces are acting here: weight of the body, normal reaction, and the friction. Okay, right. So this is the case. So in this one, what I'm going to do is, I'm going to resolve the forces at this point A. Resolve the forces along and perpendicular to the plane. I have already posted on video, mechanics video 2. In that video, I have clearly explained how to resolve the forces along horizontal and vertical components. So if you want, you go through that video, that will be very helpful for you. So here, when I resolve these forces along and perpendicular to the plane, not the horizontal and vertical line, I am resolving along the plane and perpendicular to the plane. So I am getting the equation as F equal to W sin theta and R equal to W cos theta. What is this F? The limiting friction. And what is R? The normal reaction. Then F by R equal to tan theta. So for limiting equilibrium, F by R equal to tan theta. But what is F by R? Mu. Mu is equal to what? Tan lambda. What is lambda? Angle of friction. So for equilibrium, this theta and lambda should be same for limiting equilibrium. Okay, right. So this is called, this angle is there, no? This theta angle is called angle of repose. So for equilibrium, we must have angle of repose equal to angle of friction. Theta equal to lambda for limiting equilibrium. Okay, so this is the conclusion. So what is the case we have discussed here? Equilibrium of a particle on a rough inclined plane without any external forces. Okay, so these things you have to remember. F equal to W sin theta and R equal to W cos theta for doing problems. Now let's see one problem. A body of weight 4 kg rests in limiting equilibrium on an inclined plane whose inclination is 30 degree. See, I am having a plane which is inclined at an angle 30 degree to the horizontal. A body of 4 kg weight is placed over here. So the weight is always a downward force which is acting. So because of this weight, there is a normal reaction. That normal reaction will always be perpendicular to the plane. Okay, so this is in equilibrium. So no other force is there. So obviously this particle will be sliding downwards, tend to slide downwards. So friction will be always upside the plane. So this is friction. Here it is in limiting equilibrium. Find the coefficient of friction and normal reaction. This is what I have discussed here. So I am going to make use of these two formulas. F equal to W sin theta and R equal to W cos theta. So F equal to 4 sin 30 equal to 2 and R equal to 4 cos 30 equal to 4 root 3 by 2. So simply what? 2 root 3. So the coefficient of friction mu equal to F by R equal to 1 by root 3. Okay. Then the next one, this is the second case. Here the same thing I am going to consider, but with an external force P. Okay, equilibrium of a body on a rough inclined plane under a force, and this force is going to act parallel to the plane. Okay, this force is going to act parallel to the plane. Here also I have two different cases. While applying the force, I may either try to push it down the plane or I may try to pull it upward the plane. So here in this one, we have an external force which is acting parallel to the plane. So the plane, we may try to push it downwards or we may try to pull it upwards. If we want to try to push it downwards, so when the body is sliding down the plane, the friction will be what? Upside. upside the plane. Okay, and when we want to pull it upwards, the friction will be downwards. Okay, can you see the difference? So if you are if the body is sliding down the plane, friction will be upward direction. Okay, if it is moving upwards, the friction will be in the downward direction, right? Okay, so in this case, the value of the force is P1 equal to W sine alpha minus lambda by cos lambda, and P2 equal to W sine of alpha plus lambda by cos lambda. What is this alpha? Alpha is the inclination of the plane. See, in the previous case, I have taken the inclination of the plane to the horizontal as theta, but now I have taken it as alpha. Purposely, I have taken like this because in the previous case, I have discussed the body kept on the inclined plane without any external forces. Okay, that means that theta is the angle without any external forces. So when will it get disturbed? When the theta is increased or decreased, that is the plane is either slightly upwards or slightly downwards, the equilibrium will be disturbed, no? So for mentioning that only, I have taken this angle as alpha. So theta means angle of inclination of the plane at equilibrium position without any external forces. Alpha means angle of inclination of the plane to the horizontal under the action of external force. Okay, so purposely we have taken like this. So P1, the other things have the same meaning. Lambda, W have the same meaning in all the bookworks. So P1 equal to this and P2 equal to this. So for equilibrium, the force P must be, the external force P must lie between these two. How did I obtain these two values? See, simply I have resolved all the forces along and perpendicular to the plane. Already I told you in the previous case, no, the same thing I have done here. Resolve the forces along the plane and perpendicular to the plane, equate them to 0, you will arrive at these two results. Okay, you memorize these two results for doing problems. So these two are the limiting values for limiting equilibrium. So our P must lie between these two. Suppose if you know P1, you want to know the value of P2, just you replace, you change the sign of mu. Okay, that will give you P2 value. Now let's see one problem. If the force which is acting parallel to the rough plane of inclination alpha to the horizontal is just sufficient to draw the weight upwards. See, I have a inclination alpha. Okay, I have a force and it is just enough to pull it upwards. It is n times the force which will just let it be on the point of slipping down. So both the forces I have, one is moving it upwards, one is moving it downwards. This force is n times this force they have given. Okay, what they have given? P2 equal to n times P1. What we have to prove? Tan alpha equal to mu into n plus 1 by n minus 1. I hope you understand the problem. See, I have a force which is trying to pull the body upwards and I have a force which is trying to push the body down the plane. What is the relation between the two forces? This is equal to n times this force. That is P2 equal to n times P1. Just you substitute the values and simplify, you will get the result. So W sine of alpha plus lambda by cos lambda equal to n times W sine of alpha minus lambda by cos lambda. Okay, mere simplification only. W get cancelled and cos lambda get cancelled. Now what we have? Sine alpha cos lambda plus cos alpha sin lambda equal to n times sin alpha cos lambda minus cos alpha sin lambda. So bring all the terms together. So finally what I have? Sin alpha cos lambda into 1 minus n equal to minus cos alpha sin lambda into 1 plus n. So I have tan alpha by tan lambda equal to n plus 1 by n minus 1. But tan lambda is my mu. So tan alpha equal to mu into n plus 1 by n minus 1. So this is the result that I want to get. The next problem. A body of weight 4 kg rests in limiting equilibrium on a rough plane whose slope is 30 degree. See, 4 kg weight is there. Theta equal to 30 degree. Here no external force is there. So I have to take this angle as theta. Okay, theta equal to 30 degree. If the plane is raised to slope of 60. This is what I told you. Why I have taken one angle as theta. First bookwork angle I have taken theta. Second bookwork I have taken the angle as alpha. The reason is this is the angle in which the plane should lie so that equilibrium will be maintained. If that angle of the plane is disturbed, the body will start moving either upward or downward. That angle taken to be alpha. So let me draw the diagram for the first case when it is at angle 30 degree. So when it is at angle 30 degree, I place a body of weight 4 kg. So the normal reaction will be there. So here the friction will be upward the plane. Okay, so under no external forces the body is in equilibrium. Okay, what is the second case? The plane is raised to 60 degree. So if the plane like this is there, no, if it is raised, no, obviously the particle will slide down. So instead, for preventing that body sliding down, what I am doing, I am applying a force. Okay, so this is 60 degree, I am applying a force along the plane. Okay, so I want to find what is the force required to prevent it from sliding down. So if it will tend to sliding down only, no, so the friction will be upwards, right? So this is the diagram. So here theta equal to lambda equal to 30 degree, alpha equal to 60 degree. Just you substitute the formula. P1 equal to W sin of alpha minus lambda by cos lambda. This is the value of the force required to prevent the body from sliding down the plane. Okay, just to substitute the value. So 4 sin of 60 minus 30 by cos 30. So 4 sin 30 by cos 30. So what I have? P1 equal to 4 by root 3. So this is the force required to just support the body. Okay, from sliding down. Okay, then the next bookwork. Here this is similar to the previous one, except that in the previous bookwork the force applied will be parallel to the plane. No, here the force is going to be act at an angle some theta dash. Okay, I am carefully selected the angles. Theta means in equilibrium position, angle of inclination of the plane. Alpha means when the equilibrium position is disturbed, and here theta dash I represent the angle in which the force is applied. Okay, so the other things are similar. So here the body tends to sliding down, that means friction will be upwards. Here the body is trying to move upwards, so here the friction will be in the downward direction. So in this case here P1 will be the force required here is P1 equal to W sin of alpha minus lambda by cos of theta dash plus lambda, and here P2 equal to W sin of alpha plus lambda by cos of theta dash minus lambda. Okay, so P1 and P2 as before the previous case, these are the limiting values. So for equilibrium, in between P1 and P2, the force must lie, and similarly P2 can be obtained from P1 by changing the sign of mu. Okay, then this is a practical question. What is the least force required to drag a body up the inclined plane? Okay, in the similar case, what will be the least force required? So least force required to move the body upwards means, upward means we have to take this one. This will be least when the denominator is maximum. When will you have maximum value for cos? When it is equal to 1. So when will you have cos? Value of cos is equal to 1 when the angle is 0. That is theta dash minus lambda equal to 0. That means theta dash equal to lambda. That means this theta dash will also be equal to what? Angle of friction. In that case we will have the least force to pull the body upwards. And what will be the value in that case? P2 equal to P equal to, put 1 in the denominator, it will be W sin of alpha plus lambda. So here in this bookwork you have to remember three formulas. So this is the minimum force required to pull the body upwards, and what is the direction? It must make an angle equal to lambda with the plane. Okay, we'll see one problem based on this type. The least force which will move up weight up an inclined plane is P. Okay, so let me interpret this one alone here. So I have a plane. Okay, I have a plane and which is inclined at an angle alpha to the horizontal. Okay, right. I want to move the weight up the plane. Up the plane means the friction will be downwards. So here the weight acts, here the normal reaction. This is the force P. Here just they have simply given least force which will move. It is not parallel to the plane. So let it make an angle theta dash. So what is the least force required? P equal to W sin of alpha plus lambda. Okay, so this is over. What is the next case they have given? The least force acting parallel to the plane. So this is general case. So what will be the least force required? Parallel to the plane, which will move the weight upwards. The same thing, but here the direction is parallel. We have to prove it is equal to P into root of 1 plus mu square. What is P? P is here. Let me take this force as P1. So P1 equal to, from this second bookwork, P1 equal to what? W sin of alpha plus lambda by cos lambda. So instead of this W sin of alpha plus lambda, what can I substitute? P. So P by cos lambda. So P secant lambda, but secant theta is equal to square root of 1 plus tan square theta. But tan square lambda is what? Mu. So P1 equal to P into root of 1 plus mu square. Okay, that's all. Thank you.